To better understand the quantum mechanical functions of many common types of lasers, it is best to first describe the many ways in which an electron can relax after being excited to a higher energy state.
Radiative transitions are transitions between energy levels that either involve absorption or emission of electromagnetic radiation, whereas non-radiative transitions are transitions that do not absorb or emit electromagnetic radiation. Absorption is when an atom absorbs electromagnetic radiation in the form of photons, which exchange kinetic energy to electrons and excite them to one of many higher energy vibrational levels in a higher electronic state. Following excitation, vibrational relaxation occurs when collisions between excited molecules and other molecules result in an exchange of energy that removes excess vibrational energy. Firstly, an excited molecule relaxes to its lowest vibrational state. Then it transitions to a number of vibrational states of a lower electronic state, either by emitting a photon or by collisions. If a photon is not emitted during the decay process between states of the same spin multiplicity, it is called internal conversion, which follows the relaxation of an electron to the lowest vibrational state. If a photon is emitted following the transitions of electrons between states of the same multiplicity, it is called fluorescence, and this is a radiative process. If fluorescence does not occur, a transition of an electron to a state of different spin multiplicity can occur, which results in intersystem crossing. Following that, an electron will then relax down to the lowest vibrational state. If it travels from vibrational states of differing multiplicity and emit a photon, this is considered to be phosphorescence, which takes a longer time than fluorescence.
In order to understand how lasers work, we need to learn about the rate at which atoms and molecules undergo radiated transitions and how many lasers are based on these radiated properties of atomic transitions. A phenomenological approach that describes the rates of various transitions between electronic states was proposed by Einstein at the 21st century based on a few simple assumptions about how atoms absorb and emit photons.
To describe these rates, first energy levels are assumed to be quantized and we'll imagine shining light on some amount of atoms with a two non-degenerate energy level system. If we expose all of the atoms in the sample to electromagnetic radiation at a specific frequency, some of them will absorb light and make a transition to the higher energy state. The spectral radiant energy density per frequency of light that excites these molecules is proportional to the rate of excitation from the ground state to the excited state, and is also proportional to the number of atoms within the ground state at a certain time. Following excitation, an atom will emit energy and return to the ground electronic state with either of two pathways known as spontaneous emission and stimulated emission. Spontaneous emission is when an atom emits a photon of energy at some time after excitation. In addition to spontaneous emission, Einstein claimed that you can expose an atom in an excited energy state to light and could stimulate a photon and also generate the ground state electron configuration. This process amplifies light intensity, generating a second photon per atom. In a large sample of atoms, this can occur many times, which results in a large amplification of light, and lasers exploit this amplification by stimulated emission. Unlike spontaneous emission, the rate of stimulated emission depends on the number of excited molecules. When light is exposed to such a sample, atoms undergo absorption, spontaneous emission, and stimulated emission all at once. If we consider the two energy states reaching thermal equilibrium, then the following relationship will be true, allowing for the possibility of a population inversion, which we will discuss next.
The rates of absorption, spontaneous emission, and stimulated emission that were just discussed can be summarized by this relationship. Because the Einsteinian emission coefficients are equal, stimulated emission is more probable when the population of atoms in the excited state is greater than the lower state and is considered to be a population inversion, which is a non-equilibrium situation that can actually only be achieved for at least a three-level system. Such a three-level system is illustrated by this diagram. Initially, all of the atoms are in the ground state. Now, if we expose this system with a beam of light with a frequency of E3 minus E1, it will excite the ground state atoms to the third level. This is referred to as a pump source, such as a high-intensity lamp putting out frequencies of light that are not proportional to E2 minus E1, so no atoms are excited to the second state. Once an atom populates state 3, it can either decay by stimulated emission back to the ground state by the pump source, or it can spontaneously emit back to the first excited or ground state. If light with a frequency of E3 minus E2 is implemented, both absorption and stimulated emission can occur between the second and third states. When the system is at equilibrium, the population of each level will remain constant, and as a result, the rates of stimulated emission and spontaneous emission will balance, and the change in the number of atoms in the first excited state will be equal to zero. This is considered a metastable state. Such a system has reached a population inversion and may which is considered a gain medium.
All lasers consist of three main components: the gain medium that amplifies the light, the pump source, and a set of mirrors used to direct the light beam back and forth through the gain medium. The gain medium can be a solid-state material, a liquid solution, or a gas mixture. The first laser uses a solid ruby rod as lasing medium. In the rod, the impurity chromium-3 ions are the sources of laser light and make it suitable for a population inversion. As for the pumping source, there are two ways for pumping: by optical and electrical excitation. In optical excitation, a high-intensity light source is used to excite the gain medium, just the one shown here, where the electrical excitation would involve the use of intense electrical discharges. In order to generate the high-intensity light, the light needs to be directed back and forth through the gain medium, which is placed inside the resonator. The resonator includes a pair of mirrors that direct the light through the gain medium. That's the basis of how a laser works.